Alright, welcome to lecture 4. Today we're going to be doing the chain rule. Alright, and this basically goes as follows. So you have a function f of x, and contained within it will be another function we'll call g of x. So this will be the outside function, and this will be the inside function. Now, usually the functions are written in this form. This is notationally, and I'll give you some examples in a moment. And basically, a function of this form is called a composite function. Function because it's well, it's a composition of two functions. You know, it's their join, as it were. It can also be written. This is equivalent to, and that's what this sign means. It means equivalent to f composed with g of x, where x is the variable, this is a function, this is a function. I'm pretty sure notationally this is the same, but you may want to check me on this. In any case, this means composition in mathematical notation. It's just a little circle, you know, and it'll be between two functions. So like f and g, and then you can also express this. What would be happening is you'd be taking g, and then you would map it to. Oh, I'm sorry. You would be taking like, okay, let's say that, yeah, you would be taking A to B to C, and this would be like G, and this would be like F. So then F composed with G. And this is actually a very powerful tool, thinking about functions in this form and composites in this form. And basically what A, B, and C are, they are sets. So what's happening here is we have a set A to B, right, and G is acting on it by some rule, and that's what we call G. G is pretty much called the rule. And then we have some sets B and C, and F is acting on it to take it from B to C. So this is sort of a digression, but I think it's important, and it'll help really cement these ideas if you can understand this. And this is used a lot in, I think it's category theory. I think this is used in category theory, this sort of representation of functions. And it's really cool. I recommend using this form. Alright, but anyway, so an example of a composition, a composite function would be like e to the x squared. Other examples include like ln x minus 2, and in this case your inside function is equal to x squared and your outside is e to the x. In this case x minus 2 is your inside and ln of x is your outside. So basically it's this idea of parentheses again. You know, you take, it's like your inside function, right, is inside of your outside function, such that, like, you see any variable in your outside function basically as a parentheses, and then you just put g of x inside of it, and that's where this functional notation comes from. I mean, and it's very effective for that reason. So literally, if you want to compose these two, you would write e, and then you'd have a parentheses, and then you'd put x squared inside of it. But you can put anything inside of it. You know, you could put, like, I don't know, x cubed plus 7x plus 4 inside of this, and then it would still be obvious, which is the inside function, which is the outside, because the inside function is inside parentheses, and the outside function is not inside parentheses; it's outside of the parentheses. So that's really how this sort of developed. All right, so now I'm gonna write down the chain rule, and then we're gonna do an example with it. So the chain rule is f. So if you have f of g of x, then if you want to differentiate, and we'll just say diff for differentiate it to get the derivative of, you take and basically what this is saying, you take the derivative of the outside function and then you multiply it by the derivative of the inside function. And now we're going to work through an example. So let's do one that's will be clear. Okay, so our example, we'll work with ln x minus 2 first. Okay, so our rule over here tells us that what we need to do is we need to differentiate this outside function with this ln, which is ln of x. Now I haven't gone over this, but I'm just going to sort of say it as an aside. If f of x equals ln of x, this implies f prime of x equals 1 over x. Okay? And you just need to memorize this. There's no real good way to think about it. It's pretty much just how it is. There's proofs of it. There are proofs of it out there. I recommend looking at them. I'm not going to present you with one. Okay, anyway. So our f of x is equal to ln of x in this example, and our g of x is equal to x minus 2. Alright, so if we take the derivative of f prime of x, we get 1 over x, and we take the derivative of g of x, we get 1. So essentially what our now we just plug into our formula, but first we have to compose these two. So we get ln of x minus 2, which, and then we differentiate, becomes 1 over x minus 2 times 1, which is equal to 1 over x minus 2. And yeah, so that's a pretty easy example. Alright, and now we're going to do a second one with the other composite function that we dealt with, and that will conclude the lecture for today. Alright, so we have example e to the x squared f of x is equal to e to the x, or g of x is equal to x squared. And this isn't really how people do it. I'm just basically writing this out so you can see which is which. But so this one I'm going to go a little faster. I'm actually just going to do it. So we have e to the x squared, the derivative of e to the x. So if f of x equals e to the x, f prime of x equals e to the x. And that's why people love exponential functions in calculus, because they're awesome. You can differentiate them forever and you get the same thing. Alright. So if we diff this, we get e to the x squared times 2x. And that's because g prime x equals 2x. From previous lectures we see that, and by the above claim I've made sort of here. Yeah, by the above claim I've made here, this is e to the x. So this doesn't change, but then you have to multiply by the derivative of the inside function, which is x squared. Okay, so this concludes a lecture on chain rules. Hope it was helpful.